Okay, you were asked to reverse the order of integration. And most of what I saw involved a lot of skipped steps. Were probably correct. But here's how you would write this out to show that you really had reversed the order of integration. Oh, well. I didn't even put my dy on it, so, you know, you're excused from anything you did. Okay? Okay, so just take a minute and write down what your integral would be without integrating anything. Write out what your integral would be if you reverse the order of the integration. And I apologize for not completing my expression there. Okay, let's I want to see the integral written with reverse order of integration. I don't want to see integration before I see the integral with the reverse order. So what you're going to do is you're going to have the integral from 0 to 6 with respect to x. Because when you partition this rectangular region, you understand that this is a rectangular region of 6 by 4, right? In the first quadrant, x is going to be partitioned from 0 to 6. So you better integrate with respect to x from 0 to 6. And then you integrate with respect to y from 0 to 4. And your expression that is involved with the partitioning of your interval doesn't change. It's only the partitioning of the interval, the way in which you see the partition. Okay? Well, let me kind of emphasize this a little bit. Written this way, it's like you've got the region, and if you integrate with respect to x first, and then with respect to y, it's like you're looking at strips parallel to the y-axis. Okay. Let me make sure I said that right. So when you do this final partition, you're summing up over x. And then you take all of these strips and let them go from 0 to 4. And you want to think about what I mean by that. I'm not going to go into the explanation of it, but I kind of did that last time. In this order, and we're going to do it for non-rectangular regions today. So you'll see plenty of it in this picture. The last thing you do is sum up for x. The first thing you do is you sum on y. So you take an x strip and you figure out the approximate interval on that strip. And then you add those up for all x strips. Okay. In any case, that's what you get. Now, a lot of times, you know, what I really was hoping not to see, and I don't think I saw it, so I'm happy, is people just keep the limits 0 to 4 and 0 to 6, but change the dx and the dy. Okay. Y goes from 0 to 4, not 0 to 6. And I'm not going to write it down, but x goes from 0 to 6, not 0 to 4. There's your region. Okay. So your region is 6 by 4. Reverse reversing the order of integration doesn't change the region over which you're integrating. Okay? So just, yeah, that's really pretty important. Make sure we've got that idea down. All right. Now with that, the integration is straightforward. I'm not worried about the details of the integration. Of course, if you do the details of the integration wrong, it's going to cost you a test, but what I want to look at now is what happens. Let's just take the same rectangle. X equals 0, X equals 6, and Y equals 0, Y equals 4. Let's discard the top half of it. So what we're going to integrate is over this region. We're going to integrate f of x, y over this region. Okay? Get the scale right here. When we set up our integral, we want to choose first whether we want to use a strip. Well, choose, do we start with an x increment or do we start with a typical y increment? Okay. Okay. I'll let you all vote. Makes no difference. It's no harder one way than the other. Now, with some curves, if I had a parabola here, maybe, or if I had something else, there'd be a definite preference to which increment we want to start with. Okay. And you'll see, we'll do examples of that before we're done, I think. But right now, it's not going to make any difference at all. Okay. But I'm going to let you choose. Do we want to start with an X increment or a Y increment? Thumbs up for X increment, thumbs down for Y increment. Okay. Oh man, I see a bunch of flip flopping. Get your thumbs up there. Okay. Still tied. Okay. Now what am I going to do? I don't know which way. I could break the tie, but then you're going to accuse me of bias. Why is there just an even number of you? Why aren't there 5 or 7 people in this class? Answer me that. Okay. Okay, well, this is an impasse. Let's vote again. Let's see what you get. Somebody back there is trying to mess us up. Okay. But I think before that person did what that person is doing, we had a vote for the Y. Okay. This reminds me, I call it the icing model. It's pronounced a little bit differently, but I don't remember now what the pronunciation is. Icing maybe or something like that. And it's where you have a bunch of magnets that are either pointing up or down and in a magnetic field. And if you flip one magnet, it makes all the others react. Okay, it's a profound model of magnetism. And it's very simple. You just break things into discrete units. But the entire result is chaotic. But with patterns. Very cool thing. Very easy to understand on a rudimentary level. Much more difficult if you try to analyze all the chaos. Pretty much impossible. Okay. One of my favorite things, but I never got very deep. Wrote a couple of them and watched what they did, but yeah, that's cool. Okay. So here's going to be our y increment. Okay, so this is now my delta y increment. Now my x values go from whatever sample point is in this leftmost increment up to x equals 6. So we're going to say that the sample point is I'm not getting that in the right position because my chalk is being uncooperative. Probably something to be done with the detective stupid cold on my physical coordination. So this line here is y equals y star, the sample value of y within this increment. In that case, the x coordinate of this point is what? If the y coordinate of this point is y star, what's the x coordinate? Take a minute and figure that out. But look by Crook or other method. So the question is, what are we trying to find again? Okay, again, to clarify. As always, we have a y increment. You all chose y increments. Okay. When we have a y increment, we're going to have a sample point within that element. It's going to form a Riemann sum. So this ought to be implicit. To form a Riemann sum, we have to know what happens for typical y increment. Okay. If we're going to use horizontal strips. Okay. So our typical increment has width del y. It contains point y equals y star that we're going to use. Calculate everything. Okay. So the first thing we need to calculate is what part of this y strip is within the area of integration, at the region of integration. Okay. Part from here up to here isn't. The part from here to here is within this region of integration. So we've got to know where the region of integration starts with respect to x. Okay. If all we have is constant numbers out here, all we get is rectangles. So it's clear that we're not going to have constant numbers out. Okay. So again, what x increment are we going to have to partition for this given y increment? And to do that, well, the x increment will go from x equals whatever it is, where the line y equals y star intersects this upper boundary out to x equals 6. We go everywhere from here to x equals 6. We subdivide all these little intervals. And we're going to do that. Let's go ahead and kind of depict that. So do all that subdivision. We're not there yet, but that's where we're heading. And this is what we need to subdivide from here to here. Now you might say, well, why doesn't it go from here to here? Because this is where the line intersects the lower part of the y increment. Or from here to here, this is where the y intersects the upper part of the y increment, where the line intersects the upper part of the y increment. Well, we do everything in terms of our sample point, so that when we shrink things down, everything approaches what it is at the sample. Okay. I could say that more rigorously, but we'll leave it at that idea, which is sort of intuitive. Okay. So my question then is, what's x? If y equals y star on this line, what is the value of x? I'm just trying to decide which way that's gonna make most sense to you. And I keep coming back to slope. And then some y equals 4, not y equals 6. Rise overruns 4 or 6, which is 2/3, right? Now for this triangle, rise overrun has to equal 2/3. Rise is y star. That's straight out y star. Alternatively, the line has an equation. It's the line y equals 2/3 x. That equals 2/3 y star. And it's important to be able to get this equation because you're not always going to have nice straight lines. You're going to have curves that might be fairly complex curves. And you're going to want to have an equation for that curve that you can solve to determine what x is here. Okay, well now we see that if we know our y star, we know what interval of x partition. We'll go ahead and reinsert our delta y here. And now we think of partitioning this interval. Now, I don't know how much you paid, how much attention you pay to the partitioning in the home problems. Okay. But a lot of it could be done without understanding the partitioning and knowing human nature. I suspect that you would profit from giving it a little more attention. Okay, because it's separate. Everything we do in this chapter is going to have to come back to partitioning and parameterization. Okay. So now partition the interval. We have y star to 6. Okay. Well, this is an x interval. So we can go from this x value to this x value. Right there. Subsequent number. 3/2 y star is equal to epsilon, which is less than x1, which is less than, and so forth up to xn, which equals up to 6. And now we have a petition representing this interval. And of course, within each of these increments, we have sample points. Which will ultimately be if you have foresight enough to write in the correct order. X I star, Y J star. So that's a little bit of a cluttered up diagram, but each of these increments contains a sample point, and the increment then represents the volume of rectangle. This base, this square base, or this rectangular base, in an altitude equal to F of Xi star, Yj star. Takes a little sorting out. So base horizontal strip X increments go from we have Y star to 6. Contribution of each increment to the integral of F of X, Y. I'll do dx dy because that's the order we're going to go in with your choice of what structures. Base times the height, which is delta xi delta yj times L of xi star yj star. Okay. Again, we're focusing just on what happens in front of these little engines here. And then we're just summing it up. Also, sun equals 1 to n of the sum y equals 1, 2, M, J. Before we would have the complete rectangle, we could think of just some number M of strips in this direction, some number N of strips in this direction. And the number of strips wouldn't depend on where we were, okay? But now our Y strips are going to go from here to here. So just think of a bunch of little Y strips like this, each one a little longer than the other. Each one a little shorter than the other as we move up. So we're not going to necessarily use the same M here, so M could depend on J. Doesn't have to, but in general, you'll assume that it does. Okay. And then that's going to be what? That's going to be F of XI star, YJ star, Y delta Y. Okay. And now that approaches the interval. Now, Y is going to go all the way from 0 to 4. X is always going to go out to 6. The upper limit on X is always going to be 6. But the lower limit on X depends on which J strip you're in. And we've already determined that the J strip that you're in runs from 3/2 Y to 6. So this is going to have to go 3/2 Y to 6. And whatever you're on the edge. So you see, it's critical when you're given a description of a region to be able to tell what your limits on X are given the value of Y. That's most generally done with an equation, because the geometry of the situation might be very complicated. Now, in a lot of cases, you have geometry of circles and you use that Pythagorean theorem to get those, something you should be very familiar with in first year calculus. Okay? If you remember your first year calculus, and if not, this is a course where you learn to remember. Okay? If you have more complicated curves, you lose the simple ideas of straight lines and circles. Simple ideas associated with straight lines and circles and ellipses, which are simple. Okay. So you have a lot of examples, I think, that are going to involve straight lines and ellipses. You'll have some that involve other things, parabolas and usually not too bad, but you have to be prepared for the bad stuff, for the hard stuff. You have to be able to find the equation as well. Okay. If this was the inside of an ellipse, the ellipse might be like this. Okay. Right. Well, one spot or the one like this. Then what would your Y versus X function be? That should be pretty simple. If you know your conic sections, depending on whether you reviewed them when we reviewed them. Okay. And we didn't spend a lot of time reviewing them, so we're supposed to know for the calculus. So you might have to go back to that to review in order to do the manipulations, but they're not difficult. It's not an insurmountable obstacle. It's just something that might take you a little bit of time, and you probably feel like you don't have time. It's life. Some big name entrepreneur talked to I think it's probably was a graduating class at Stanford, or a bunch of incoming freshmen at Stanford. And he said, I wish you an ample amount of pain and suffering, because that's how you learn. Okay. And Stanford top-notch students, arguably the best students in the country, although there are two other institutions that argue that too, MIT. Okay. My institution can make a good argument that it's not going to fly in place at Stanford and MIT and a few others. Okay. This argument is as good as it used to be. When I left, they just went down. They couldn't recover. I think they have a power reaction. So put your patient with it. Basic pre-calculus to get the equation to these curves. Okay. And then you plug that in to the calculus, to the multivariable calculus. And if you can do the pre-calculus, then you can get the limits on your integral. But on the limits of the integral, a whole different order of business. And if you have to do both at the same time, it's 4 times as hard. Okay. Be prepared for a little pain and suffering. And if you survive, it's much better for it. I'll do everything I can to make it less painful and sufferable, less painful and more sufferable. But it comes down to again, dirty work. Okay, so let's do an example. Let's go back to I forget what the function was we did last time. I don't want to do this function because it just makes more sense in integration. It's not more difficult. Let's take a plane. X minus y plus 7. Well, once we've figured out what the limits are by just doing a little geometry or a little pre-calculus, a little algebra, hopefully just a little, we see that we ought to get the integral of 6 2/3 y 4 of 2x minus y plus 7 dx dy. Again, this tells you essentially what the contribution to the integral is of a small horizontal strip. Got a question? Probably did something stupid also. That's almost given. Come on. Okay, well, somebody wanted to dispute like 2/3 here, especially since I used 3/2 here and I got 3/2 over here. And the 3/2 came from the geometry for this region, okay, where the x extent was basically greater than the y extent. Okay, that's a little bit of oversimplification. But if you think about it, it should be clear that this should be 3/2 instead of 2/3. Well, that's kind of a mistake I would make even if I was 100%. So I'll fully own that. But yeah, free house. Okay. Now, we just do the integration. Integration thing. Well, the one person came down with a number. But there are a lot of correct looking steps. Something that looks a little suspicious. So let's be careful. Let's get an idea of what we might expect to get. Let's just think about what the values of this function would be. At 0, 0, this function gives us 7, right? I don't have a lot of room, but I'll just draw. I'll just draw a little triangle. And I'll just indicate the altitude above this point ought to be 7. About this point here, where y equals 0 and x equals 6, altitude ought to be 19. Talking about coordinate to z coordinate comes out this way, right? And at this point, where x equals 6 and y equals 4, we're going to get the same 19. We're going to subtract, or we're going to get 15. Now, it looks to me like the average value of this function is going to be closer to 15 or 19 than it is to 7. And the area of this region is going to be half of the area of the rectangle that encloses it. And the area of that rectangle is 6 by 424. So it'll be like 12. So I'm guessing that we ought to get something like about 140 something. Yeah, I'm just guessing maybe 140. Now it could be 100, it could be 107. Okay. So one thing we can do is just common sense, look at the numbers and then do the integration and see if it comes out consistent with the numbers. If not, one of two things. We set up the integral wrong, or we made a mistake in the integration. Okay. Now I'm going to try not to make a mistake in the integration, which is what we have the integral from 0 to 6, and we see the integral of with respect to x. And I'm derivative of 2x is x squared. That's 7x plus 7 y. Okay. See how easy it is to make mistakes and you're not thinking. Okay, we take the derivative of this with respect to x, and we want to do that in our head just to check our step because there's so much pain to go through to get the final solution and then go back and debug it that we want to get it debugged right here because we're capable of making those mistakes. Okay, no matter how careful we think we're being. I'm more capable of it than you are these days, but still. So derivative of x squared would be 2x, derivative of x, y would be y, derivative of 7x would be 7, derivative with respect to x. And then this is evaluated 3 down to y, 4. And when we finish that, then we go ahead and integrate with respect to y. Well, okay. At 4, we get 16 minus 4y plus 28. Let's evaluate of x equals 4 minus the quantity 3/2 y quantity squared. And I'm gonna so is it my minus sign's correct. If we minus the whole thing that I get when I substitute 3/2 y in 4x. And I'm going to get this, and that's integrated with respect to y. And then I think it close this parenthesis. And then be careful, go 0 to 6. 16 and 28 is 44. And minus 4y. If we square 3 halves y, we get 9 fourths y squared. And if we subtract 3 halves y from 9 fourths y squared, we get 3/4 y, I think, but I'm going to check that out. 3/4 y squared. Does that make sense? Okay, again, I'm going to get a y squared both ways. I've got 3 halves, which when we square gives me 9/4. And then 3 halves is itself 6/4. 9/4 minus 6/4 is 3/4. So I kind of believe that, although I remain skeptical. And then I can take a chance. I'm going to have a negative 3/4 y squared. And then on my y's, I'm going to have minus 4 and minus 21 halves. Now 4 is 8 halves, negative 8 halves minus 21 halves is negative 29 halves. And then I have plus 44. Now, does it make sense? But and it's negative 21 halves, negative 29 halves y. Does it make sense that my y terms should be negative? Yeah, because y is negative here. And bigger y is going to tend to make this thing less high, which contributes less volume. Okay? Just like my x terms were predominantly positive, okay, except the one that was multiplied by y, and that goes back to what I just said. It's worth thinking about things like that when you work these things because you get deeper insight. You don't just get an answer, you gain insight. Okay, well, I don't have much room to finish this. That's probably kind of small. Okay, I'm going to get negative y cubed over 4. And I'm going to get negative 29 y squared over 4 plus 44 evaluated between 0 and 6. This looks to me as though it's going to come out negative, which is probably not a good thing because I calculate the oh my goodness. You see what I did right at the very beginning? What are the limits of my interval here? 3 halves y to 6. What did I write? 3 halves y to 4. So whoever was accused me about that 3 halves y is to blame. No, I wrote that down well before you caught that. Okay, so that's got to be 6. This has got to be 4. That ought to mitigate a lot of this. Okay, well, we can work through the details of it. And you probably should to see if my estimate of an average height on the order of 10 with an area of 12 gives me something in the order of 120, give or take. Do it carefully and don't do fundamental things wrong. very beginning. Um, I'll correct a lot of this. Uh, six minus 6y. And I apologize for it. That should be a 6y. Guys on. On the upper limit, so that's okay. And this is this minus 12y over 2 plus 21 minus 21y over 2. That's not into 33. This 34 becomes 64. Like that. And then the force still does what it does. That should be magical here. Something's wrong there. Anyhow, that's how you separate. Now, the other side of that coin is what you get when you do this should equal what you get when you reverse the order of operations. And that's what we're really leading here. So I probably went on about that both in error too long. See, right, not there. Oh, got to be a half of this, so I'm not going to be able to refer back to this, but if I want to reverse the order of operations, then I have the same geometry. But I'm going to choose vertical shifts. Delta X on X star. To do it using proportionality because I've got some similar triangles. And what I'm going to get is y goes from 0 to 2/3 of X. Using the equation. If X equals X star, y is 2/3 X star. So here it is. So I partition with X from 0 to 2/3 X star. So we do first of all, our X strips will go from 0 to 6. And then our Y strips. Let me write this up. Number one. We can describe our region. Zero less than or equal to 6. Zero less than or equal to Y less than or equal to 2/3 X. That makes sense? X could be anything from 0 to 6, and Y goes from 0 up to 2/3 of that. Okay? Our partition is X's go from 0 to 6, our X increments go from 0 to 6, and for each X increment, Y goes from 0 like this. On the ith interval, X goes from something to something here, and Y goes from 0 up to 2/3 of Xi star. The interval is the interval from 0 to 6 of the interval from 0 to 2/3 X of whatever our function was 2X minus Y plus 7. Y dx. So that reversing the order of integration really requires that you pretty much sketch out some schematic of the region and reason out what happens if you choose to do vertical strips versus horizontal strips. Whichever one you choose first should be the same as you would get with the opposite choice, but the interval is not going to look the same because it's going to be a little more complicated. Make sense? Okay. Okay, well, we're out of time. I really wanted to talk about polar integrals, but I think we have to put that off on Tuesday.